Okay.
Hi,
Okay.
sir. Good evening.
Good evening. Good evening. Okay. So we'll just wait for a couple of minutes. So this is week 4 live coding. The problems are put up on the portal. You can have a look at it. We will go problem by problem anyway. But if you are here and if you're ready, yeah, you can start looking at the problems. Yeah, we'll just wait for a couple of minutes. Okay, everyone, before we start, yeah, just wanted to know how the course is going on. How is week 4? How are you finding the topics? Yeah, anything you want to share? Okay, I think everyone is okay, all good, just the pacing is okay. Yeah, either it's very easy for everyone or very difficult. Okay, so how was week 4? Since we are doing week 4, so week 4 we looked at graphs, right? BFS, DFS.
Implementation part is quite tough, sir.
Okay, okay.
Finding some difficulties in package.
I would term it as tricky rather than tough.
Okay, okay. Yeah, Parth is saying, yeah, week 4 was manageable. Yeah, week 5, yeah, that is going to be a challenge, Parth, because the schedules are also tight. Even we don't know how. Yeah, you will have to just give your best. That's all. Okay, so were you able to implement the codes which Professor Madhavan gave in the lectures? Did you try it out? Did you start going through the assignments and all of that? Week 4?
Trying to do this, so getting the approach, but yeah, as I mentioned, the implementation is quite tricky.
Okay, okay, okay. All right. So, okay, I think we can start. What I'll do is, yeah, I'll start sharing. Okay, can you see my screen? So we'll do coding. Along with that, I have a presentation also. You can go through it as well. So or what you can do is go to joinpd.com and type in this code. EML MBJ. If you want, I can put it on the chat also. Okay, one student is connected. Others also can go to joinpd.com and type this code, or you can go to the link I've put in the chat. Okay, just wait for a minute and then we can start. Okay. Okay, let's start. Okay, so everyone, welcome to week 4 live coding. So this week we looked at graphs, right? DFS, BFS, topological sorting, DAGs, right? And I hope all of you have gone through the lectures. And okay, so let's start coding. Okay, so the first problem, it's available here also. If you go to, I'm sure all of you know where to go. I'm just reminding you. Yeah, so this is the first problem, right? I will give you all a minute to go through either the slide or on the portal itself. Yeah, just read through the problem, look at the sample input and the output. Yeah, I'll just wait for a minute. Yeah, then we can start.
Sir, can you a little bit zoom it?
Okay. Okay, I don't think that can work. But what you can do is go to the portal. No? I'll share the link. I don't know.
On portal also, sir. It is looking very small, sir.
Oh, is it? Okay, wait. I'll increase this. Is it better now?
Yes, sir.
So can you share the portal link in the chat?
Okay, sure.
Thank you.
Yeah. I hope it is correct. Yeah, I think so. Yeah. Okay, others who have just joined in, there is a peer deck slides also going on, so you can log in there as well. Yeah, I've shared the link on the chat. Okay, so I hope all of you have read the problem. Okay. Now, so what is it asking for? We have to create 2 methods, right? There's something called in degree of a list, right? That it accepts an adjacency list. And what does it return? It returns the in degree of each vertex as a dictionary. So you have a dictionary, you have the keys which are 0 to n-1, which are each of those nodes, and the in degree value, right? And this in degree underscore mat is also the same. It returns the same output. The only difference being the input here was an adjacency list, and the input here is an adjacency matrix. So I hope all of you are aware of the difference between the adjacency list and matrix. Any doubts in that? Okay, I hope no doubts are there in that. Okay, so now, okay, and I hope all of you are aware of what an integrity is, right? So let's see if this is better. Okay. Yeah, so look at this graph, okay, on the right. Can you type on the chat what is the integrity of 8? What is the integrity of 8? Integrity of node 8. Okay, I see 3, 4, 4, 4, 4. Any other answer? Okay. Okay, can someone unmute and say why 4? Any of you? One of you.
Sir, the incident arrows on 8 are 4 from 1, 7, 2, and 0.
1, 7, 2, and 0, right? Yeah, very good. So what you have to do is just look at the node and see which all arrows are coming in towards it, right? So that becomes the integrity. So we have 0, 1, 2, and 7, right? Yeah, so I hope that's clear. So what is the integrity of 0 then? Integrity of 0 is 1, right? Okay, since we just have an arrow. So if you see this double arrow, what it means is that there is an arrow going from 0 to 8. There is another arrow coming from 8 to 0. So there is one incoming edge and hence it is 1. Okay, good, good. All right. All right. So how will we go about solving this problem? Okay, so let's think of integrity underscore list first. Okay. So we have something known as the adjacency list, right? So I want you all to think about what does this look like? Okay. Yeah. Now I think you all can start coding. So the question is, what does this adjacency list look like? Yeah, just spend a few minutes thinking about that. Okay, let's see if I can do something here. Is my screen visible?
Yes, sir.
Okay, so we are looking for, yeah, so we want to create something known as this function integrity underscore list g list. Okay, yeah. So what does this G list look like? Okay, that's the first question we have. Let's say this is, yeah, we have a definition here, but let's say G list. Okay, I think we have the answer here, right? In the input itself, you can see that G list looks something like this, right? So you can see the nodes 0, 1, 2, and 3 are the keys of a dictionary, and each of them have these, each of them maps to a list. And what does that mean? So what that means is 0 has arrows going towards 1, 2, and 3. All right. Now what we have to do is we have to calculate the in degree of each of this, right? Yeah. Yeah, I'll give you some time to think about it, code it up, and then I think some of you who are trying can share your screen. Let's see how you're going about doing that. Okay, I'll just give 5 minutes. I'll just pause for 5 minutes. You all can start coding this function, definition of in degree underscore list, right? Okay, I'll give you around 5 minutes. If you all have any doubts, you can unmute and ask anytime. Okay, Snehal is asking, are we supposed to write an optimized program or a naive approach would do? Let's start with the naive approach. Let's see uh, what the naive approach is, and let's see if we can optimize it, right? So Sanjay is asking, can we use matrix.shape? Yes. Yeah. So for the adjacency list, I don't think we need it. Yeah. For the matrix, we can. Yeah. Yeah. We can use matrix.shape. Okay, I guess on the portal NumPy is not available, so maybe we can't use that. Okay, so anyone, would you like to maybe you can share your screen or talk about how you are writing the function? Yeah, anyone, even if it's not complete, it's okay. We can just get an idea of. All right, Madhav, yes, go ahead.
So just a second.
Yeah, sure.
Yes. So mine was kind of a naive approach. Yeah. So let me just share my screen for a minute.
Sure, yeah.
Where is that option? Yeah. So is it visible?
Yes, it's visible. Yeah.
Yeah. Okay.
Yeah, you can. You can talk about the code. Yeah.
Yeah. Yes. So first I wanted all the edges like as tuples. So what I did was I iterated through the given dictionary glist, and for each key there would be some child nodes. That is, let's say in the given example, the child node of 0 is 1, 2, and 3, and for 1 it is 3, and 2 it is only 4.
Right.
So for each child node, I would be putting it as a tuple, I and j. So j would be iterating through the child nodes, and I are the parent nodes each time. That is the
Okay.
keys.
All right.
And after that, I have all the edges as tuples. So here, so I will be running through all the tuples, and let's say I have a return dictionary which I have to return this. They are asking as a dictionary format. The return value should be a dictionary, so which I have declared it here. After that, for each tuple, that is the second value is the child node and the first value is the parent node, right? So in that case 0 1, and the 1 is the child node and 0 is the parent node. 0 2 means 2 is the child node and 1 is the parent node. And
Right.
here indirectly what we are doing is for every child node we are counting how many parents are there. So whenever I come across an edge, I just see which is the child node, and for that particular node I increment the parent, the count of parent.
Got it. All right. Okay, let's pause there. Others, any suggestions? Is this code correct? Will it work? Anyone would like to share anything? Can we make it a little more simpler? Anyone?
Sir, I think we can do it much simpler in the sense that we can simply, for the matrix, we can simply go ahead and just see that particular column and see how we can just count and add the numbers.
Matrix, so, I do it in particular column. I need to add some more if cases. That is, if double equal to 1, I didn't do it.
All right.
So, yeah.
All right. Yeah, we are talking about list. Yeah, in case of list, Priyanka, what do you think?
So list also, actually we could only go through the dictionaries and just see if it is there, although it will be quite expensive, but then we can just see through all the lists, for all the dictionaries, for all the keys. If it is there, then that's it. if that number is there.
Okay, if that number is there. Okay, okay. All right. So processing using a nested for Rajdeep. Yes, yes, go ahead if you can share.
Yeah,
Okay,
let me
thanks,
show.
Madhav. Yeah,
Yeah.
the solution is fine. It's correct. It looks correct. Maybe there is an easier way. Let's see.
Yeah, there is an easy. Yeah.
Yeah, someone wanted to share. Yeah, Rajdeep, go ahead.
Sir, is my screen?
Yes, yes,
Okay.
it's visible. Yeah.
Okay, sir. Just one second. Sir, this is the first code for integrity, calculating integrity where adjacency list is being used. First, we initialize the dictionary, and then for every element in the dictionary, in the list, we initialize its value to 0.
So ID is a dictionary which
Will store the integers.
which stores the integrity for each of the nodes, right?
Yes, sir.
Okay.
And then I use a nested follow. I go through first of all every node, and then go through the neighbors. I mean, of every node in the second for loop, and then I increment it by 1.
Okay. So let's pause and let's just see what's happening. So you're saying for I in G list. So what will happen is it will iterate through each node in my graph. Okay, that's fine.
Yes, sir.
And for each of those nodes, so what is the value for each of these nodes?
Sir, it's a list because it's an adjacency list, so it will be pointing towards other nodes. So we'll end up calculating the integers of every nodes inside, like what? Suppose A is pointing to B. There's a node from A to B.
Right.
Then it will increment the integer for B. That is what is happening here.
Right. So I hope all of you understood. So what we're doing, the strategy is we take each node. For each node, what is the value? It is a list, right? And that list represents the neighbors of the ith node, right?
Yes,
And so what that means is that these are the incoming edges. These are the incoming edges, right?
Right.
So that means that I is pointing to J, and hence J's in degree should be incremented by 1, right?
Yes.
So that's what you're doing.
Yes.
Okay. Anyone? Does anyone have any doubt?
No, sir, I also approached in this way only because the dictionary key and value concept. So value is basically what are the values holding, that is the integrity to that key of the other dictionary. That is the only thing.
Exactly. Yeah. Anyone? Does anyone have a doubt in this? I hope it's clear. Do you want me to explain? I hope the integrity is clear. If not, I can explain again.
No, sir.
Right? Looks good. Okay. Good. So then, similarly, then, yeah.
Yes, sir.
For matrix,
this one for adjacency matrix. It's almost the same process. Initialize the dictionary first, where we will store the value of integers of every node, and then I catch the length of the list, which will actually give us the names of our nodes from 0 to n-1. And by iterating through from 0 to n-1, I can initialize the value of the integers of all the nodes to 0 in this, and then I use a nested for loop again. I go through 0 to n minus 1. Then if gmat index j I is equal to 1, then I increment for I. I do not increment for j. This is the only important part here, because while we are iterating through this, I will remain constant. J will only keep on changing, and in an adjacency matrix, indegrees will be getting the indegrees from our columns, and only if we increment for I, will get the indegrees of all the nodes. So first, suppose if it's I is equal to 0, we get for 0, 0, then 1, 0, and then 2, 0, and on and on till n minus 1, 0. So we end up getting the indegrees of the first node, and then similarly for the rest of the nodes. And at the end, we return the dictionary. That's it.
All right. Okay, Rajdeep, looks good. Anyone has any doubt in this?
But Rajdeep, hello.
Yes,
Yeah,
yes.
yeah.
Rajdeep, just show your code.
Yes, dear, just one second. Yeah.
Rajdeep, to check the indegree, we browse through the column, right?
Right.
So you are actually changing this gmat j comma I.
Yeah.
Right. So this j comma I means it is keep on changing the row value.
No, I'm actually like, see, when we are going, when we are inside the second loop, I remains constant, right?
Yes, I remain constant.
J keeps on changing.
See,
so we are actually going along the columns. Had it been I comma j, then we would have been going along the rows. Actually, if you
okay, right, because you are moving 1, 0, then 2, 0, then 3, 0,
right.
keeping. Yeah, okay.
Yes, ultimately, yeah.
Yeah. Correct. Okay.
Anyone has any doubt in that? Did you understand that part?
Sir, I have a question. This is Chandra Prakash.
Yeah, Chandra Prakash, go ahead.
Sir, in the code which was just shown above, when we put up for adjacency list for I in G list. So the G list is a dictionary, right? So we should put for I in G list dot keys in the for loop for the range, or should we just put for I in G list?
Yeah, that's a good point. I think you need to include the keys, right?
Yes, sir. That's the question or doubt.
No, I think naturally it
Sir,
takes
it
through
actually
the
works
keys.
without mentioning the keys as
Yeah.
well.
Yeah, I think both. Yeah, it works without the keys also, but then yeah, and later on you're mentioning it with the index, right?
Yes. Yes,
okay.
sir.
Okay, sir.
Yeah.
Sir, I have a question.
Yeah, Shruti, go ahead. Yeah.
Sir, I don't know. We could just have appended the adjacency lists and counted how many times each of those occurred. No, why didn't anyone do it? I'm just asking, is that wrong?
Sorry. What is your question?
So we were given an adjacency list in the first part. So we could just have appended all the values which were sublists again and counted the number of occurrences. Even then we would have got the answer, no?
Okay. What do others think? Will that work?
Yes, sir. I think that was also possible, but maybe it will end up having what the same number of
that will be out degrees, isn't it?
Yeah, that is out degree, right?
Okay, let's just check.
Or am I getting it wrong? Like, am I getting it?
That's in degree only, no? What is given is actually
I think she means
degree.
to say that for every node there will be a list. So if we end up appending those lists together.
But only appending that thing will not give you the format they are asking for this output.
No, then we can just count the occurrences of each
Like
of
she means
those.
to say that if we append 1, 2, 3, then 4, together and then we count the occurrences, right?
Yeah, sir, it will work, sir.
Yeah, it will work.
Yeah, it will also work.
We can
Yes.
count each number, sir.
Right. So what you're saying is take each of these lists, right? Append it to form a very big list.
Yes, yes, sir.
Maybe sort it or whatever and count the occurrence of, let's say, how many times 1 occurred, how many times 2 occurred, how many times 3 occurred.
Yes, yes.
But that will only give how many out arrows have gone, right? It's not telling you by each vertex
No. That
how
will
much have
give
come
in.
in.
That will
No,
give
it
in
will give
only.
you in, no. So what we are given is actually the out.
Yeah, because 3
but
will
there
come
one
2
more
times.
thing we have to be careful is we have to take a like count of those whose indices are 0 separately.
There is a problem in this method. I think it will give only the in degrees of those which are there in the values of this dictionary. I mean, 0 is not will be counted.
Yeah,
Then,
so later on, after you have the big list, you can take these keys and make a fresh list, fresh dictionary, no? When you're counting.
We can initialize all the values to 0 and then we can start
And then, yeah, that's what I meant.
Right. Yeah, I think it will work. Yeah.
But I think Rajdeep chose a very simple and straightforward approach that way.
Correct. Yeah.
This one actually, which Joe suggested, I think might be costly because you are going to count again and again on the same list.
Yeah,
But
I think
it's
complexity
better
will
than
increase.
2 for loops, I guess.
No. Just think of counting again and again on the same list. 2 for loops is just.
No, counting. Why do we have to count it again and again? So I will iterate through the big list just once and increment all the values in dictionary as I see them.
Oh, okay, yeah.
So it will be, okay, that's a good question. Let's think about it, no? So let's look at, is there a graph here?
But again, you have to come back in your dictionary for the keys which is not in the list.
So as somebody mentioned, the dictionary will already initialize with the keys that have already been given. So and then every time we see an element, we just increment the dictionary. So
That is the
it is
same
actually
thing.
far more
I think
efficient.
same approach was done by.
Same thing is done by Rajdeep, right? That is the way. First initialize all the keys as 0.
No, Rajdeep actually used 2 for loops, right? That's not what I meant.
No, 2 for loop, but not in series, in parallel. Means it is not a nested for loop.
No, I think it
I
was
saw
a
nested for loop.
It was nested for loop.
Oh, the second one is nested for loop, right?
Yeah. So for matrix, it's a nested for loop. But what about the adjacency list?
That was also.
Yes, it was a nested loop, but was it like order n square?
So order m plus n.
Yeah, it was order m plus n, right? Rajdeep, can you share your code? Yeah.
Yes, sir. 1 minute. So should I share the screen again or can paste it in the chat?
Okay, sure. Yeah, you can paste it in the chat. Yeah. All right. Okay.
अभी तो चढ़ाई थी यार क्या चढ़ाई थी हाँ उधर तो बिछाई कब की बिछाई मैंने यहाँ तो नहीं उधर अपने मिली उस दिन की
All right. Okay, so we have these two functions, right? So here you can see that Yeah, it looks like 2 for loops and it will be looks like order of n square. But is it actually order of n square? Because we are just going through the length of each of these, right? So it will be the order of the number of edges, right?
So the worst case will still be n square only. No?
Sorry?
The worst case will still be n square only, no?
Worst case, will it be n square or will it be m plus n?
Plus n, sir.
Sorry?
It is m plus n. In the worst case, even it is m plus n.
Yeah.
Because the second for loop, I am going on to the only up to the G list of I, not the entire dictionary. That is the difference.
Exactly. Yeah. Is that clear?
Yes, yes, sir. Although the I list could potentially have n minus 1 elements.
No.
No, it
The
can't.
I list is every key is having some list. So if I browse the dictionary with all the keys, it is the addition of all the values of the key. So if that is m, I am browsing the dictionary I for n times and adding the value that much m. So it is n plus m times the maximum browse.
Okay.
Yeah. So what? Sorry, who asked that question? I forgot your name. Yeah. So if 0, so it's like a fully connected graph, right? If 0 is connected to all the other nodes, 1 is connected to all the other nodes, 2 is connected to all the other nodes, then what will happen?
Then it will be n into n minus 1.
Oh, then it is, sir, n plus n, that many of n will be added.
How many of n?
If everything is connected with everyone, I found every edges. That's what you are saying, right?
Yes, yeah.
So suppose there is n vertices and everyone is connected with n times. So I will adding n of n times that.
Exactly. And that is?
20.
Then
n square, no?
Not n to the power n, right?
Not n to the power n.
No, not n to the power n.
N into n, right?
n square.
N square. Yeah. So yeah. So that is the thing, no? So in practicality, what happens is the graphs which we usually see are not fully connected. And that's the reason why an adjacency list might work better most of the time, right? But in a matrix, it is always going to be n square, right? Because we are always iterating through all the rows and all the columns, right? So that's the only difference.
That means in adjacency list, we are skipping all the zeros, only
Exactly.
considering the edges
Yes,
one.
yes. Okay, so I hope we spent a lot of time in this, but I hope you all understood, right? How to go about doing it. Okay, let's move on to the next one. Okay, let's move on to the second problem. Okay, yeah, I'll just give you some time to go through the problem. Is it visible? Is the problem visible? Or you can go on the portal and check it also. Problem number 2. Yeah, just spend a few minutes just reading the question, looking at the sample input, sample output. Let's see what we can do. All right. I hope you all went through the problem. You're getting some idea. Yeah. So one thing which you should do when you encounter problems like this is, try to understand the problem, before jumping into the solution. What is actually the problem, and think about some things, some problems or some algorithms which you have already seen in class. Does it resemble some of those problems? Okay, so for example, yeah, so maybe you can write on peer deck, this problem is similar to which of the topics we learned in week 4. Okay, yeah, let me see if I'm getting some responses. Okay, so you have gone through an algorithm which which can help you solve this problem. Okay, let me see what the responses are. Only 4 of you have responded. Others respond down peer deck. Okay, many have responded on chat. Okay, let me see the responses also. BFS, DAG, BFS search for minimum ops, topo sort, BFS and DAG seem to be the dominant ones. Okay. Okay, so all of us know that it's going to be a graph traversal, right? Because we have to start from somewhere and we have to reach somewhere else, right? So we have to traverse a graph. So my question is, okay, most of you have said BFS, but why not DFS? DFS is also a graph traversal algorithm, right?
But the DFS may not return you the shortest path.
Sorry?
DFS may not return you the shortest path.
All right. Why do you think so?
Because, sir, I'm suppose from where we start, the very next is available the destination that I want to reach. But I can go down because I'm not exploring that level completely. I'm going to the other deeper level and come back, and later on I can explore that. So in that way, I may not be in.
Actually, there is a way from DFS, like you can calculate all the paths from a source to destination and return the minimum path.
That's an exponential algorithm.
Yeah.
Yeah. We won't get into those details now. That you will see, I think, mostly next week. Yeah. So what you all said is correct, right? DFS, it does not guarantee the minimum, I mean the shortest path between two nodes, but BFS will help us do that, right? So the traversal which we have to do is BFS. So so if you see, yeah, so let's just look at the BFS algorithm. Let's look at nodes. Where was it? It was yeah. All right. So if you recall the lecture, yeah. So one implementation which Professor Madhavan showed was, is it here? It will be here somewhere. Yeah. So if you remember this BFS, what we were doing is we are just maintaining a dictionary of visited nodes, and we are just returning that dictionary. Okay, will that work in this case? No, right? Because we need some more additional information, right? And okay, so in addition to visited, we need some more information. And so that's why in the next one we looked at recording paths, right? So along with visiting a particular node, we also find out which is the parent, right? So we also find out which is the parent. Okay, I hope this algorithm is clear to all of you, right? What we are doing is we are maintaining two dictionaries, visited and parent. Visited initially is set to false because we haven't visited any node, and parent of all nodes are set to -1, right? And what we're doing, and we are starting from a node V, right? Let it be some node, and we set that to true, and then we add B to a queue, right? And we continue adding and removing things from the queue till queue is empty, right? Till the queue is empty. And what we do is we look at all, so for K in A list of J, so we look at all the neighbors of the element in the queue, right? And if it is not visited, we visit it, right? We set it to true, and parent of that node, right? We know the parent of K, whatever K is, that is actually J, right? And then we add K to the queue, and we continue this till the queue is empty, right? So I hope this is clear. Okay. Yeah. So for example, we'll just quickly see this. So if you have to start from 7, right? 7 is added to the queue. Then we look at all the neighbors of 7, which is 4, 5, and 8, right? And 4, 5, 8 are added to the queue, and they are set to true, and their parents are set to 7, right? Then we look at 4 and visit its neighbors, and then we add 0 and 3. And for 0 and 3, we set the parent to 4. Yeah, and then we continue this till the final list contains all the parents, right? And we have visited all the nodes. All right. So with this information, now let's go back to the problem. So if you look at this algorithm, we have this visited, we have this parent dictionary, right? But here we need something more, right? Right. So if we start from 8 and if we want to reach 7, we also need to output out a list which will give me a path from 8 to 7. Right. So the question is, what do we do after we get path and level, right? So we have got the path or the parent information, we've got the level information. What do we do? Okay, I think I missed something. Yeah, so the next algorithm, in fact, right, it talked about the level also, right? And what level tells me is, you know, from the starting vertex, how far is a particular vertex, right? It's the same as the previous one, right? You're initializing it, you know, you're checking if queue is empty or not. And if, so in addition, instead of visited, we have something known as level, right? So level of all the values are initially -1. Then we, for the particular starting node, we set it to 0, right? Then we look for all its neighbors whose level is -1, which means in a way that it is not visited yet. And we set it to level of j, right? So initially, let's say j is v and v is 0. Whatever is the level, we add 1 to it, which means that from j to k, there is 1 hop. That's why we increment it by 1, right? And parent the same, right? We add parent of k is j, and then we add it to the queue and continue, right? So, any doubts in this algorithm? All right. So, yeah. So this is doing the same thing, right? Let me just quickly go through this. So we start from 7. 7 is added to the queue. We look at all its neighbors, which is 4, 5, and 8. Now, we not only add its parents as 7, but whatever was 7's level, which is 0, we add 1, 2, 4, 5, and 8, which tells us that from 7 to reach 4, 5, and 8, you require 1 hop. Similarly, from 4, you look at 0 and 3. So 0 and 3, the parent is set to 4, and the level is actually 1. Just we continue this till we explore everything and we get the levels. Okay, any doubts in this? Okay. So let's say we have this path and level and all of this. What is the additional things we need to do, right? Yeah. So we need to get this path, right? 8, 9, 1, 3, 7. So this tells me that from 8 I go to, so if I want to start at 8 and reach 7, the shortest path is 8, 9, 1, 3, 7. And that's the output I want to get, right? Yeah. So I'll give you some time to think about what strategy do we use to get the path. Okay, spend some 5 minutes to look at the algorithm and see what additional things we need to do to get the path. Okay, I'll give you 5 minutes. Okay, everyone. Any strategy? You can type in your response on the peer deck. Yeah. Any ideas coming to you how we can do this? Have you started coding? Okay, no responses on peer deck, on chat.
So to get the list means path traverse, do we need this level? Because
Okay.
once we have the parent dictionary, there itself we can trace back the path, right?
No, you will have to make a decision at that junction that which way you have to go. That might give you the longest way to reach that node.
Once I have the.
But we are doing a breadth first, no? So it will breadth first search. So it will give you the shortest path, right?
That is why I'm thinking is that since the parent dictionary we are making through this best for search, now I have all the information from which node to which node, what is the path, because it is ultimately that key value combination will, if I can able to trace it, I will eventually get that path from where to where.
Okay. So hold that thought. So sorry, I didn't get your name.
Shomit, sir.
Shomit. Okay. Shomit. So okay. So you're saying that we actually don't need level. Parent will do, right? Yeah. Let's think about that. So what you're saying is we can. Yeah. So we somehow we have the parent information, and using that we can do something, right?
Yes, sir. This is what I think. Sir. I may be wrong.
Okay.
Samit,
yeah.
Same thought actually came into my mind also. But when you check the Bfs algorithm, while creating the parents dictionary, you have to depend on the level because in the after while loop in the there is a loop for k in the a list j. So here you have to check whether the level k is -1 or not. Then only you can make the parent dictionary. So this is required in that stage.
No. Actually, there is 3 algorithms as in his lecture shown.
Yeah.
I'm talking about the second algorithm.
Correct.
When you only tracing the path, not the level, how far it is, you are not checking.
Correct.
I just interested to know if the node I am searching, if it is true, then what is that path I can trace it. In the second algorithms are told this thing.
Correct. While you are identifying the path or in the parent dictionary, so you have to take a base of the level. You have to follow the level. You just go through this the label and parents algorithms part, then probably it will be clear.
No, I think what Samit is asking, can you see my screen? Is this algorithm sufficient to calculate the path? In this, we don't have level, but we have a visited this thing. Is that enough? Right? Okay. Right, Shamit, I think that's what you are asking, right?
Yes, sir. Yes.
Okay. We'll think about that. Okay. Let me see what responses we have got. Not certain. Okay, run is coding still. Okay, I don't want you to give the entire algorithm, but can you briefly tell me what you will do?
Yes, sir. I'm audible?
Yes, Shyam, go ahead.
Sir, I'm just basically finding all the paths one node to another and just taking minimum of the length. Suppose there are 10 paths. I'll just take the one path whose minimum. And
sorry, can you repeat?
I'm just finding all the paths from one node to another node.
All okay, but we already have the
And
start and the end, right?
Yes, yes. From starting to end, I'm finding all the paths, and just I'm taking the minimum one.
Okay, yeah. So how will you find all the paths?
Can you scroll back to my code which I've sent to you?
Oh, okay. This one, right?
Yeah.
Okay. Yeah.
For this first, I'm just
So
making
what's
a.
happening here?
Should I explain?
Yes, sure.
Okay. I'm starting from def minimum, where I'm taking a list starting point and ending point. Then I'm making a list visited, and every time for a list key, I'm making visited false. Then I'm making two paths, one paths and second all paths, two list. Okay, then I'm calling my function paths, which will give me all the paths, which I will give it to a list as t visited that I have made it earlier. All the values of visited false, paths initially empty, all paths initially also empty. Then it will call the paths function.
Okay.
Yeah. In path, when I will enter into the path, I will make my starting point true, and I will append the path, append the s, the starting point, into my list path. Then I will check if the starting point and ending point are equal. I will make a copy of path and append into the second list all paths. And otherwise, if it is not equal starting and ending, I'll just make it that for I in a list S, it means that all the vertices which are connected from S, they will, if they are not visited, then I'll again call my function path. It's like a DFS. Okay, then when this will happen, suppose that I'll get my first path from 6 to 7. Suppose I have visited all the things 6, 4, 2, 7. Everything is done, and starting and end is equal. It will start backtracking. From here.
कॉल कर रही हैं यार, समझ में नहीं.
Sorry.
I don't know. Someone said something. Okay, then.
Okay.
I just backtrack path pop. The last value I have added to the path dictionary, I'll just pop it up, and visited at s is equals to false. All the vertices that I have visited, I'll make them false, so I can again go through them. It's a long and elastic code, I know, but it worked.
Okay. I'm just thinking, will it give? Okay, so you're checking for the minimum of the paths, right?
Yes, minimum.
Yeah, I was just thinking whether it will give all the paths, and from those, so paths is returning a list of. Oh, so paths is returning a list of all the paths. Huh?
Yes. It's actually not returning, but it's making all paths here.
Okay. It's making all paths there. Okay, so let me try to summarize what you're saying. So you are going to call this function mini with the start and source and a destination. You are creating, you're having a path and an all paths. Path is, okay, path is actually, yeah, it is for that particular start node. You are looking, yeah, you're going through a DFS way and seeing and adding it to paths. Okay, and what if there is no path from S to D? Hello?
Yes, sir.
Okay. I think it might work, but I'm not sure about. Yeah, just I think we'll have to check the corner cases, right?
Yes, sir. We just have to check the
Okay.
corner cases.
Okay, okay. Anyone else wants to share any other strategy? So, yeah, so that was one solution where we kind of looked at the source and the destination, tried to find all the paths using DFS and looked at the length of the minimum path, and that was the output, right? So to summarize, that was the strategy you tried, right?
Yes, sir.
Okay, Shyam. Okay. Is there any other strategy which someone else has tried?
Sir, am I audible?
Yes, yes, yeah.
Once I calculated the parents dictionary from BFS, I made a list called path. I first put in the ending vertex. Then while path of 0 is not equal to the starting vertex, I keep inserting the parent of the 0th vertex in the first position of path.
Okay. Yeah. Is your code like, have you written something? Do you want to share?
I put it in the chat, sir.
Sorry?
I put it in the chat.
Oh, okay, okay. Let me see. Okay, okay. See this. So what you're saying is, okay, so you have the parent and the so you have the parent and okay, so you have the parent dictionary, right? Parent dictionary is ready, right?
Yes.
And E is the ending vertex, right?
Yes.
Okay. So you're saying while path of 0 is not equal to S.
S is start.
S is the start. And what is this PAR?
Oh, that's
parent. Okay, this is the parent, right? Yeah. So if parent of path 0, which is the first in the list, okay, then you are inserting that to the path, right? Okay. Others, any comments on this? Will this work? Okay, okay, let me just check the, okay. So this is it. So what you're saying is we have the parent ready. Now if we have, yeah, so we start, let's say we are the start ending as 7. So now we look at path of 7. Okay, path of 0 is 7. 7 is not equal to 8. Then we look at the parent of 7, right, which is 3. And parent of 3 is not equal to -1, right? So then we add 3, right? Otherwise, we return. Okay, why return S?
That was in the question. It told us to return a list containing only the starting vertex if there is no path to it.
Right. So, okay. So in a way, you're looking at each, and if the anywhere you see that it is -1, then you're immediately returning S, right? Right. Yeah. So what this algorithm is doing is it is looking at it is starting from the end. Okay. For that end vertex, it is checking if its parent exists. I mean, if there is a parent, and if it is there, that whatever that is, right? That is getting the parent of that is inserted to the starting position. So actually now path will now be 3, 7, right? Now we look at the parent of 3, which will be 1. So then we insert 1 to the starting of path. So it will be 1, 3, 7. Then it will be 9, right? Then we have 9, 1, 3, 7. And then finally we have 8, which is then we finally add 8, and once we have that, we return, right? Yeah, I think this works. Does anyone have a doubt in this?
Sir, if there are multiple parents, then what happens?
Sorry?
If there are multiple parents, not just this question, but let's say if there are multiple parents for a single node, then will this code work?
Yeah, so the thing is, in BFS, is there a possibility for multiple parents? What do you think? Okay, so what do you mean by multiple parents? Yeah, I'm understanding. For example, let's say if there's a node 3, it can be that 4 is its parent, or even 5 can be its parent, right? Yes, I think that's what you're asking, right?
Correct, yeah.
Yeah, but remember, in the BFS algorithm, for each node, you will exactly have one parent, right?
Thank you. Understood.
Because how can we guarantee that? So if you see, yeah, in the algorithm itself, you can see that we are looking at the neighbors of a list of J. so we are looking at the neighbors of J, and in whichever order it comes, it can be in any order, right? So yeah, so your question of, yes, if I run it once, maybe the parent of 3 might be 4. The second time the parent of 3 might be 5. But for a particular run of BFS, you will only get one of, you will, for a particular node, its parent will only be a single node, or it won't have any parent. Is that clear?
Yes, sir, it's understood. I have one more question now.
Yeah, sure.
Let's say there were multiple parents, and let's say it's a question in the quiz and there are multiple parents. So let's say if I run it on my end, I get some other BFS tree. I mean, the tree, the parent is different. And in the quiz, the accepted result has a different parent. So is that a possibility?
I don't think that will happen. Yeah, I don't think that will occur. So one reason being, I think the BFS, what we are doing, especially even for the problem, it's a directed graph. So for a directed graph, that issue won't be there. Yeah, so I don't think that will be an issue. Yeah.
Okay, no, thank you, sir. Actually, I'm not aware of all the edge cases, so that's why I'm asking these questions.
Yeah.
Sir, this approach we got it. So there is one gentleman had shared the path approach, the first one. So similar question we had in practice assignment where we have to list all the paths. I think second assignment was there. So if that approach you can explain us, because the same solution was there in some websites as well. I think Geek for Geeks and all. But I'm not able to understand that. So if someone can explain that, that would be great.
Okay, sure. Yeah. So I was thinking maybe let's go to the next few problems, then I'll come back to that. Right?
Sure, sir. Thank you.
Yeah. Okay, so to summarize, I think what strategy will work is, if we are using BFS, right? Using the parent information, right? What we have to do is start from the end, right? And then go back to the parent until you reach the start node, right? Until you get, parent of that is -1, then you will get that. And if you are not able to get, if you are not, if the parent of any node in that path is -1, that means you have reached that means that that from that node, it's not the start node is not reachable. That's why you just return the start.
Sir, that means we do not.
Any doubts?
That means that we do not need any levels, right, for to do this.
Yes, we don't need, man.
And one more thing, sir. This returning is, we can die, since if we maintain two dictionary, visited and parents, from the visited dictionary for that particular node, if the value is false, I can directly say ki return is.
Exactly. Yeah.
Okay.
Yeah. So do we need level? It doesn't look like, no? Because if we get, just if we are able to check for this condition, or if we have the visited thing, I think it should work. Yeah.
And if we set a counter, sir, in the while loop, till from the every iteration I can increase one counter, and that will give me the level. If I
In this code, you're saying,
in this code itself. See, if it is now I am tracing back from the end to the first to plot the start to end how I am going. If I set a counter, I can get the level.
Level for only that path, right?
Only for that path, right?
Yeah, that's fine. Yeah. All right. Any doubts in this problem? All right. So we'll go to problem 3. Problem 3 is similar. Okay. We won't go into details of problem 3, but yeah, you can spend some time reading this, and somehow it is related to problem 2, or is there some other way which you can solve it? Yeah, I'll give you 5 minutes to go through problem 3, and then we will briefly discuss the strategy, and then okay. Any Any strategies, any ideas? I hope the question is, you all have understood the question. Any doubts in the question? So for example, here, if you see, right, if you want to start, you have to start, let's say you want to find a root between 0 and 1, right? So one path is 0, 6, 1, right? So now 6 is excluded from that. So then the other is, let's say 0, 2, 3, 1. So all these nodes are excluded, right? Or 0, 2, 3. Yeah. Yeah. So any ideas? How will you go about solving this?
The
Is it
best approach in this case would be following DFS.
following?
So depth first search.
Okay, why do you think so?
Sir, because like we can start with node and we can go on, like we first find its neighbors, then we choose to explore one of the neighbors, and then we can again come back to, like, let us say 6, and see whether it takes it back to neighbors and whether we can reach 1 from there. So I think depth first search would be I think ideal for this.
Okay, but will it give you the minimum set of nodes between two nodes?
Sir, no, but what we had wanted was the maximum number of possible routes. So we will be able to get maximum possible routes through that.
Yeah, but there is a condition, right? Without going through the same node again. Okay. So for example, if I take using depth first search, if I go to 0, 2, 3, 4, 5, 6, 1. Okay, that's possible, right? In depth first search, right?
Yes, sir.
So then I will just get one path. You're getting it?
Yes, sir.
We can do this thing. We will conduct the breadth first search only, but every time we will exclude one node which is having a direct connection from the 0 to that node.
No, I didn't understand that. So
see, first we will run this with all the nodes 0, 2, 3, 4, 5, 6, 1. And if we run this breadth first search, we will get a shortest path between 0 to 1.
Okay.
Then in the next iteration, I will eliminate.
Okay, so that means the shortest path will be 0, 6, 1, right? Or 0, 3, 1, for example.
Right.
Okay.
Yeah.
In the next iteration?
In the next iteration, I will delete one of the node, that is 2, from the graph.
But why did you choose to delete 2?
Oh, no, not sorry, 2. The shortest path 0 to 3, 1. I will delete 3, and I will run the breadth first search again to find any other shortest path is there or not. And similarly, if I encounter that, sorry.
Not looking for shortest paths.
Sorry, Dhruv, were you saying something?
I'm saying we are not looking for shortest paths, are we?
Now, if I run the Bfs search for any graph, that will automatically give me the shortest path. That is why I'm saying shortest path.
But it's not asking that. It's asking the number of routes that are possible from node 1 to N1 to N2.
But with one condition that we
Yes,
shouldn't.
Yeah, go ahead.
We should not go the same node again and again while choosing the shortest choosing the path. That means 0, 2, 3, 4, 5, 6, 1, 1 path, and we can't use again 0, 2, 3, 1 because this is again 2 and 3 I am crossing twice. This is the condition there, the problem.
Correct. All right.
Yeah, sir. I think his what he is telling is correct. We have to go for finding shortest path every time, so that we eliminate minimum number of nodes in each step, and so that we can maximize the number of possible routes that we actually attain.
Okay. Yeah. Okay, that's a good summary of what you just said. No, so what you're saying is we will do a breadth first search starting from 0, right? And so we'll do a breadth first search, and similar to the previous problem, we will try to find a path from start to end, right? That's what we did previously, right? We have a start and an end. So in this case, that is N1 and N2. We will get a path, right? So for example, let's say the so we have N1 as 0 and N2 as 1, right? And we use the problem 2 algorithm. And what we'll get is the shortest path from 0 to 1, right? So let's say it is 0, 3, 1. Okay. Yeah. Now, Shamit, Priyanka, what you're saying is, what should I do?
Sir, we should, in each step, we should find the shortest route so that we can minimize the number, because whatever route we will take, those nodes we will have to delete in the next search. And so thereby we will minimize the number of
So you're saying now
nodes that we will
delete 3, right?
Yeah.
Delete 3 from the graph, right?
Yes, sir.
And
Then
run BFS, run problem 2 algorithm again. And I don't want to say delete, let's say I'll exclude, right? And run problem 2 algorithm again, which is the shortest path from 0 to 1, right? So now I might have, since I've removed 3, I might have 0, 6, 1. Okay. Now I remove 6. So now I will have, what will I have? 0, 2, 4,
3, 4, 5, 1.
No, 3 is also removed, right? 3 and 6 are removed. So 0, 2,
4, 5, 1.
4, 0, 2, 4, 5, 1. Okay. So I remove 2, 4, 5. Okay. So till when should I continue this?
I think
Till we stop finding roots to the end node.
I think we have to run it for all the neighbors of 0, right? Only for all the neighbors of 0. Because if
Correct.
0 has no neighbors left, then we can't find a path.
Correct. Right.
Right. So we run it for all the neighbors of 0. So it can be 2, 3, and 6, right? Or another condition can be, yeah. So we are excluding nodes, right? And if we just end with the start end1 and end2, that means we have exhausted all the nodes, right? And then we can count. Will that work? Right. So the strategy is, yeah, use the problem to algorithm to find the shortest path from end1 to end2, right? Which all are the intermediate nodes, right? The next time you do BFS, don't include those nodes. So it's in a way you're excluding those nodes at each step. You continue this process until you have exhausted all the nodes in the graph except the start and the end. Is that clear? Any doubts?
I have a doubt.
Yeah.
So suppose I had a graph where there is a path which I can reach only from 2. I can't reach it from 3, but it's a very long path. But still, it's like advantageous for me to take the long path instead of taking a path which has some sort of intersection with another neighbor, right? Because if I delete that neighbor, if I delete the second shorter path, if the path from the second neighbor which I was talking about has only that path to 1, then I'm actually like removing 2 possibilities and just adding like 1 to the answer instead of taking the bigger path, which basically was the only way I could reach to 1.
Okay, so what you're saying is there is a longer path to reach to 1.
Not for this particular example. Like
Yeah. Okay. Yeah, I'm seeing what you're.
So suppose I can give an example. Suppose, okay, we're starting with 0. Okay, I can't draw it. So like suppose I'm starting with 0 and the next level is say 2, 3, 4. And from 2, I have a path like 2 to some 7, 8, 9, 10, and goes on and reaches 1 finally. But from 2 and 3, I have a path which goes to 6 and then comes to 1. So basically, in the first step, it will go 0, 2, 6, 1, and then remove that path.
Okay.
But now, if there's no path from 3 to 1, I'm stuck at 3. I can't go anywhere from 3. There's no path from 3 to 1. But instead, if I had taken the longer path from 2, I could have taken 0, 3, 6, 1 to reach 1.
Okay.
So it's like always, it's not advisable to take the shortest path, right? Even though.
Yeah. I think.
Can you explain once more the argument?
The one that it's not necessary to take the shortest path.
Yeah.
Yeah. Okay, let me just try to draw something here if it's possible. Yeah, so what you're saying is, let's say I have something, oops, something like, so you have a node here and a node here, and from 0, you're going towards 1 through that, right? And let's say we have a node like this. Yeah, is this example correct? And I don't have this edge, these two edges. Is that what you're saying?
If there are multiple paths from each node to one, it would still work because removing one would not affect the other.
So for example, here, one path between 0 to 1 is 0, 3, like this, right?
Sorry, sir?
No, one path can be 0, 3, 2, and these two nodes and 1, right?
Yes, sir.
So if we are saying if we take the shortest path, let's say it was 0, 3, 1, for example, and when I exclude 3, that means now I don't have, I can't reach these two nodes, right? Is that what you're saying, Ashwin?
No, but I think the assumption is that you're always choosing the minimum, the minimum number node in the sense that 2, 3, 4.
Sorry, sir, I was disconnected.
Minimum numbering. But what I understood from the lecture that actually
Voice is breaking, sir.
Yeah, even I can't hear. Hello.
Hello, am I audible?
Yeah, now you're audible. Yeah.
Yeah, sir, what I was telling, sir, in the lecture, what was told that choosing the minimum numbering, like numbering here, numbering would matter. For example, if you have 0, 2 in the new scheme that you have drawn, let us assume that the first 2 and after that 3 and then 4 and then 1. Let us assume it is something like that. So the assumption here is that if you go from 0 to 4, this route, then actually you end up deleting both 2 and 4. So you do not get the second route actually here, which you should have got. But then probably we can choose how to choose the node. We can make the choice maybe in a better way. Otherwise, actually, you will get what you should get. You will get, if their path is like that, you will get the same number. You will get maximum number 1 only. You will not get 2, which you should not actually. If you cut this route and you are not allowed to go on that route again, then yes, you will get only number 1. I mean, maximum routes available to you would be 1 only in that case.
Yeah, because if 3 is included again, that would contradict the question. If 0,
Correct,
3, 1 is
correct.
being included,
Correct,
then
correct,
0, 3, 2 can't be included because that would contradict the question.
Yes.
Yeah. Yeah, so that's why I think if we follow that strategy, I think we will get the maximum number of, subsets of the vertices, right?
Sir?
Yeah, Ashwin.
Actually, like I drew a case. I drew
You
the
will
case
always pass through this number 4.
Yeah, Ashwin, do you want to share?
Yeah, can I share my screen?
Yeah, sure.
So is it visible?
Yeah.
Okay, sir. So as per the strategy, first we'll get this 0 to 1.
Okay.
0 to 1, which is fine. So So that will be removed. But the problem is, next step it will give me 0, like so okay, sorry. Instead of I'll do this. I'll do this for the timing. So suppose it gives me 0, 5, 6, 1.
Okay.
So because we can't predict, right? Because which will
Correct,
be
correct. Yeah.
So then this common node 6 is out of the picture. This junction node which was there, which was connecting like 3 and 4 also to 1, is gone now.
No,
Instead of
6
that,
we are
if I
not
had gone
removing,
this
a
long
friend.
path,
We are removing 5, not 6.
we have to remove all the nodes, right?
No.
Which are in the path.
Adjacent to the starting point.
No, we'll have to remove 6
You have
also.
to remove all the
Can I
nodes.
clarify?
He's correct. He's right only.
Yeah, can I clarify, Ashwin? Actually, the thing is, the question is asking, you have to find unique paths between the starting node and the end node in which no intermediate vertex is repeated. So if I find a path 0 to 1, and then I find a path 0, 5, 6, 1. Now I don't care about the part 0, 3, 6, 1 because 6 is being repeated in it.
Exactly, yeah. So what I was saying was, from 5, instead if I had gone the longer path 0, 5, 8, 11, 1, I could still have gone from 0, 3, 6 to 1. That would be giving me 2 paths. Instead, if I go 0, 5, 6, 1, I'm removing 6 also the next time, which means now neither 3 nor 4 can go to 1.
No, Ashwin, it's correct only. See, the point is you have bottlenecks at 5 and 6. You assume it's a road. So if the road at junction 5 and junction 6 is dug up, let us say, you will not be able to reach, even if the longer route, 8, 1 was available to you. These are the bottlenecks, and I think this is what we were trying to achieve by this program. And I think it is giving you the correct answer only. So you can choose to take 0, 5, 8, 11, 1, or you can choose to take 0, 5, 6, 1, but ultimately you will end up losing this 5, which will be, sort of, your bottleneck that way. So you see, you have your weak link in your design anyways. So that way you have to see, actually. This is just what I wanted to say.
And I think to encounter this problem, that is why we have to find the minimum shortest path, not 0, 5, 8, 11, 1. If we will find shortest path, then we will get all maximum.
Yeah. So the okay. So Ashwin, you are saying so how many paths will we get? We'll get 0 to.
So as per this algorithm, we'll as per the one which you had written, you will get 0 to 1 as the first path.
Yeah.
The second one would be 0, 5, 6, 1. And that's it. We won't get any more.
Why you will not get 0, 3, 6, 1 and 0, 5, 8, 11, 1? Why you will not get that? You will get that actually.
Because
if we follow
1 and 0, 5, 6, 1, then the others are not connected to 1 by any node. There's no path from 3 or 4 to 1.
No, but Ashwin, but you could have taken 0, 3, 6, 1. Then 5 would be available for you to count for the next third route available.
But the BFS can't identify which to choose. Like when there are several paths which are like shortest, you can't really say like which. For example, if even if
to encounter this problem, Priyanka ma'am said that to encounter this problem, we have to first of all we will have to find out shortest path. So you should not choose after 0 to 1. You should not choose 0, 5, 6, 1. You should choose the shortest path so that we can get maximal routes.
All are same length through 0.
But Ashwin, there is 3. I am seeing the 3 route, even in your case only. One is 0 to 1. This is first route. Then you are saying 0, 5, 8, 11, 1, right?
Yeah.
If that would be more optimal. Because now I can do 0, 3, 6, 1 or 0, 4, 6, 1 also, which would give me an extra path which initially I wasn't getting.
Yeah, sir, means how to choose means we should go from 0, 3, 6, 1 or 0, 5, 6, 1 in between these 3.
Yeah, I think
how to choose between 3 to 5, sir.
Yeah. So that I think the algorithm does not tell us which to choose.
Yeah, sir. In that case, we will lose 6. Then we will have only 2 paths.
Sir, but what I wanted to say, what I understood
from
the lectures, what Sir Madhavan sir was telling, that the numbering approach you can choose, appropriately. So probably we might have to choose that he chooses the minimum numbering of node. So if he chooses the minimum numbering of node, you will end up choosing 0, 3, 6, 1, and then you will get the third route also. So it will depend upon the strategy that you choose.
Sorry, you got muted. Yeah, no, but see that is very unpredictable, right? In the example,
Because I could anyway swap 3 and 5, and then I would.
You can serve.
Yeah, sir. Yes.
Correct. Yeah, that's a good point, Ashwin. I'm also not sure how we can tackle that. Yeah.
Sir, what I was, again, just what I think I got disconnected in between.
Yeah.
So what I want to say is that we can choose to choose the nodes appropriately, the strategy, which node we pick up, next node to explore, which node we pick up. That will be the strategy that will decide, whether we can actually explore all the 3 routes or not. So if we choose to, in this case, if we choose to choose the minimum, node. So minimum node here would be 3 and not 5. So you would like to explore 3 first. So once you will explore 3 first, then the 5 route will be available to you, and you will maximize your this thing. So I think it will depend upon the strategy that you choose to traverse which nodes each time.
Yeah, that I agree. But like what Ashwin was saying, and what I also think, if we had swapped 3 and 5, then choosing 3 would not have been the optimal solution, right?
Then we'll have to change our strategy in coding. That is what I
Then, sir,
understood from
we can choose this strategy that whichever node is minimum outgoing edge. Like in the case of 3 was only one edge outgoing, but 5 was 2 outgoing edges. So we can choose minimal outgoing edges in that case. So we can get maximum part.
So choose minimum outgoing edges.
Because 5 was 2 edges, na, sir, outgoing. And 3 and 4 was only one outgoing edges.
Right.
So by that, I think if Ashwin will share, then.
All right. Yeah. I'll get back to you on that. I think. So there are corner cases. No?
And if you connect 3 and 4, then
5 has 2 outgoing edges and 3 and 4 has only one outgoing edge.
Yeah, but if you connect 3 and 4, then 3 also will have.
But if you delete all this thing, means in between 0 and 1, then you are always going to lose some of the available path. Always lose.
Yeah.
Because it is emerging from one point and again converging, and you are deleting one converging means a lot of emerging point you automatically get deleted. Whatever strategy you will take, you will lose that path.
Yeah. So this is a good point. I think put this up on Discourse, so we'll discuss this in detail. Yeah, I didn't think about these cases. Yeah.
I was thinking like, suppose we could label all the nodes as reachable from which of the neighboring nodes of 0. So in that case, if from 2, I prefer to go to a node which was only reachable from 2, and I continue that for all the vertices. I would preferentially get a path which was reachable, like which composed of nodes which are only reachable from 2. Because if there is no such path, then I'll be forced to take a path which is intersecting with a vertex of 3 also, right? So then, but the only issue is I'll have to like keep track of which all from which all vertices I can reach that particular node, and that will be again increasing the complexity.
Yeah. So it's not a straightforward problem, no? All right, I think we are running out of time. We'll move on to the next one. Yeah, we'll just
Did
quickly.
anyone try coding this on the current portal? Like, did it work?
I didn't try because implementing itself is
Same.
it was difficult to implement, and also it would go into n squared for all cases. So.
All right. Yeah, but I think in the portal, I think at least the examples which are given, I think that the BFS strategy might work. I also have to check. I'm not sure. Yeah, but you made a valid point, Ashwin. Right? Okay. Okay. It's already time is up, but we just go through problem 4, right? Yeah, just spend a few minutes reading problem 4. Okay, everyone. Yeah, looking at the problem, do you think it's similar to something you have learned?
So it sounds similar to topological sorting.
Okay. So, okay. Why do you think so?
So because it's basically like you have to like sort of eliminate, dependencies and then go on seeing, which tasks can be performed later. So sounds very similar to topological sorting.
Right. Right. So there is this dependencies within a task. So it's like a diagram directed acyclic graph, and you have to return the order in which the tasks will be done. Right. So we have to do some topological sorting on a directed acyclic graph, but there is one additional thing which we have to check out for, right? So there is a preference list, right? So there are some interesting things. So preference is the task sorted in preferred order. So the initial tasks are more preferred compared to the final tasks in the preference list, right? So yeah, so let's quickly look at the algo, right? So what happens in topological sort is we we have a list, right? And what we do is we first of all, here we are calculating the in degree for each of the nodes, right? And then we are looking at the nodes which have no dependencies, right? We start from there. So we look at the nodes which have no dependencies, which implies we look at the we look at the nodes which have 0 in degree, right? And in this case, we are choosing the minimum from that, right? And we are appending it to the topological sort list. And once we select that vertex, we remove it from the graph, right? So I don't know if it's here somewhere. Yeah, okay. We can go into it now. Yeah, so we remove it from the graph and we update the in degrees of all its neighbors, right? And we do this until all the we do it for all the rows, for all the nodes, and we return the topological sort list. Okay, so if we have this algorithm now what and where should we make the change? So one thing is this has an additional parameter, right? We have a preference list here, right? So we have a preference list here. Yeah, that's an additional thing. What changes are required, or what strategy should we use? Yeah, so what we know is it's a variation of the topological sort algorithm. What is the variation, and will you use some data structures or some strategy to implement the solution? Okay, yeah, just think about it start coding if you want, right? This is the algo for topological sort. What changes will you make?
So
yeah, Neeraj, yeah.
So in the second for loop, second line, j is equals to minimum of.
Yeah.
So what we are getting here, I'm not able to understand. In a single line, it is written. That's why.
So this is a list comprehension thing, right? So what is happening is it is there is a for loop, right? And in that, so it is iterating through the columns, right? And it is looking for this condition. If in degree of k is equal to 0, then it is adding k to the list. Okay, so what is happening is there is an expression, there is an iteration, and there is an evaluation. So these three things are happening. So it will iterate through some things, and if the condition is satisfied, it will add that to the list.
Okay, sir. Okay. Thank you, sir.
Yeah, maybe is it clear, or should I explain?
Yes, sir, clear.
Okay. So the expanded thing for this will be for k in range of columns. If in degree of k is equal to 0, add k to the list. That is the long form. Okay. Yeah. Any thoughts on what needs to be done? You can write. You can share your responses.
Sir, I think when we are just getting that second, when we are getting the element which has in degree 0, we have to get all the elements and then we just find if it's minimum in the preference list. And that's the element we take for next iteration.
Right. Okay. Let me just go to the algorithm. Yeah. So all these parts remain the same. You're saying, like, of course, we have to calculate the in degrees, right?
Yes.
Yeah. So where do you think the change will come?
So I mean the list comprehension.
Here.
We just remove the minimum. We get all the elements here, and among all those elements, we have to find what is the minimum in the preference list.
All right. Okay. So you're saying,
like which element in that J list has the minimum index in the preference list?
Right. Correct. I think that's the only change we have to do.
Right. Find. Right. So what we do is we look at the preference. So we look at the Ks which come, right? And we look at its order in the preference list, right?
Right.
And whichever is the minimum, we choose that value of J, right?
Correct.
Right. I think that's the only change which is required. Did everyone understand that?
No, sir, some more explanation is required.
Okay, okay, sure. So, okay, let me just... okay, yeah. So is this understood? I mean, the topological sort, the normal one is understood, right?
Yes, sir.
Okay, okay. So I have written somewhere. Okay, let me see. Is my screen visible?
Yes, sir.
Okay. So let's see what's happening. Huh? See this here. So what I've done is Topological sort, what do? We compute the in degrees, right? We maintain a queue of the vertices with in degree 0, and whatever is the vertex which we get with in degree 0, we choose the minimum one in this algorithm. Right? We chose the minimum one, but there we have to make some change, right? So, so we are computing the in degrees here, right? Initially, all of them are 0, and for each of the neighbors, right? We calculate its, we append the in degree by. Right? Is this much clear?
Yes, sir.
Yeah. Now, okay. Now what we have to do is we start with so we start with all the nodes with degree 0, right? So let me take, is a graph given in the example? All right. Yes. Yeah. Okay. Yeah. So now what we do is we take the node with. Okay. So here in this, can you tell me which nodes have in degree 0?
Sir, 0 and 1.
Right. So now the option, now we can choose either 0 or 1, right? Right?
Right.
Yeah. So what we do is we add 0 and 1 to a queue. Okay. Now the option is we can choose 0 or we can choose 1, right? But that choice depends on whether the preference list, right? We have the preference list. Let's see. So the preference list will have something, maybe 0 will be first, then 1 will be there, or it will be 1 will be first, for example, and 0 will come later, right? So we have to check, right, which comes first. If it's 0, we choose 0. If it's 1, we choose 1. Is that clear?
Yes, sir.
All right. So that is what this code is doing, So for each of these elements, whose in degree is 0, we look at its index in the preference list. Okay. So for each of the nodes with in degree 0, so if you, let's see what's happening here. So Q contains all the nodes with in degree 0. So for each of that element which has in degree 0, I look at its index in the preference list. Okay. So I create a tuple S which has a set of which has a list of tuples. Okay, which is a list of tuples which has the index in the preference list and the element. Is this clear?
Yes, sir.
And what I do is I just sort it. And the 0th element or the first element in the list, right? That will be the, yeah. So if 0 comes first, so then 0 will be the 0th element. If 1 comes first, 1 will be the 0th element. So whichever is the 0th element, I choose that and that becomes my, or that I add that to my task order first.
Yes, clear, sir, clear.
Anyone else? Do you have any doubt in this? And then I continue the same, right? I decrement the in degree of that, and for all the neighbors of J, I decrement it by 1. I remove it from my. So, for example, let's say the preference list was this, right? If it was this, that means I choose 1. So that means I decrement. I make this as -1, so it's outside the graph, and I also decrement its neighbors in degrees, right? So that means this node goes away and this also goes up. That's what I'm doing here, right? And then I again continue the process till the length of the task order. Yeah, so till I don't exhaust, all the lists in all the elements in my A list. So then again I empty the queue, and then I look at all the nodes which have in degree 0. So now in this case, which of them have in degree 0? Yeah, I don't know. Yeah, sorry. So then now I'm left with only 0, right? And then again I look at the neighbors 2, 3, and 4. I look at 2, 3, and 4. They are added to the list, and I check the index of 2, 3, and 4 in the preference list. Whichever is minimum, right? That will, once I sort it, that will come first. I take that and I continue doing this. Okay, yeah, you can try doing this. Do you all have any other strategy which you have tried out?
Why can't we just traverse through the preference list because it's already sorted and find the first element that's of in degree 0? That's the element that we are going to remove.
Sorry.
So you go through the elements in the preference list because the in degrees are getting updated, right?
Right.
So you pick the element that has now in degree 0.
From the preference list, you're saying?
Yeah.
Okay. So
because it's already sorted, so I'll get the element that needs to be removed because preference is the order in which we need to go.
Okay, I think that should work. Wait, let me just check out. Slow note. What do others think? Will that work? Okay, let me just share my screen. Okay, so you're saying I go through the preference list for each node. I look at the one which is in degree 0. I choose that, and then I do the update.
Yeah.
Right. Yeah, I think it should work. So let's try it now. So in this case, yeah, I think 0 is not there anyway. So 0 is in degree 0.
And 7 is in degree 0, so we'll pick 7.
7 has out degree 0.
Sorry,
Right?
out degree 0. Sorry.
Yeah. Yeah, 0 is not there anywhere. So 0 has no incoming edge. So 0 will pick. So we look. So there's only one element. So 0. We choose 0. Right now, 0. Then 1, 2, and 3 are its neighbors. So we.
So their degree becomes 0. In degree becomes 0.
Their in degree decrements by 1. Right?
Yeah.
Right. So 2, 1 का in degree है 1, 2, 2 minus 1, 1, 2 का है, yeah, 2 has in degree 0, will have in degree 0, and 3 will have degree 0. So 2 and 3 hai, right?
Yeah.
Now what will I do? Now again
Now
I will. Sorry?
Now I will go through the list and choose 3 because 3 comes before 2.
Yeah. Yeah. So how is it? Yeah, the order you are starting from the preference list and checking.
Yeah.
Whereas what I see, yeah, I think it should be okay.
Oh, but we'll choose 2, right? Because 3 is appearing at 2 places, so in degree is 2.
Sorry, Pan.
We will choose 2, right? In the second iteration.
Yeah, because 2 has only in degree 0, right?
Yeah.
Yeah, sorry. Yeah. So, yeah. Okay, Snail is asking complexity. What do you think is the complexity? Any thoughts on that? So we are calculating the in degree. Then, okay, let's look at the code here. Yeah, so here itself we are getting an m plus n kind of thing order. And what about here? We are adding elements to the queue. Yeah, here also it's an order m plus n, which we are running n times, no? Right?
Yeah.
So it looks like n into m plus n, which is like n square. Yeah, I also think it will be n. Yeah, it will be n square. All right. Sure, you can try this out. I think this is pretty straightforward. Yeah.
And so by the way, someone tried the BFS code and it is passing all the cases in the question. So I think there might be a flaw in the question, maybe.
Oh, okay. Yeah, even I looked at the question and yeah, the BFS, I think. Yeah, maybe the inputs which we gave were, not. Were not of the flavor.
Test cases.
Yeah, the test cases. That's it. Yeah. But you will learn these things, in week 10 and 11 and all about network flows and all of that. I think it's week 10 or 11, yeah. And so there all these, flow from the source to the destination, which is the minimum path. All of those things will come. So we'll explore that a little more in detail at that time. Okay, so yeah, I hope these 4 questions gave you an idea of, what was taught this week. Yeah. Any other doubts in these 4 questions or anything else? Okay, I think we can close then. So okay everyone. So yeah, please attempt the questions, like see if there are any issues, and yeah, then see you next time. Any other doubts, anyone? Okay, let's end the session then. Okay everyone, see you. Bye.